Okay, so the master theorem, thank you for letting me know so that I can do this, come back in and out, and we'll try it as many times it takes, okay? So the master theorem can only work with this form of recurrence. So you ended up with a recurrence where the input size is being divided by some value, and A could be 1. You could have one recursive call, doesn't matter, for any constant, okay, other than 0. So if you are falling into this form, you can use the master theorem. And I am. Look, I have an example of a recurrence for some algorithm that I have written. I have 2 if n is less than 3, 2tn over 3 plus n. You can replace this 2 with theta of 1 and with theta of n. That's totally fine too. Okay, so basically, let me get back to here. We can actually determine, looking at the recurrence that I have here, 2t n over 3, you know, A is 2 and B is 3. And the C is, let me tell you what C is. C is the degree of my polynomial. So what is the degree of this polynomial, n? The question is for you.
1.
1. So that therefore C is 1. Okay, because we're going to use our master theorem. I have to determine what is A, what is B, and what is C. C is the degree polynomial. So if somebody said theta of n, the polynomial degree is 1, right? If somebody said theta of n squared, they put it in there, the degree of your polynomial is 2. So therefore C is 2. So now I have determined A is 2, B is 3, C is 1. I'm going to use this formula. So I explained it where f of n is theta of n to the cth power. So this is my f of n right here. In this case, this is my f of n, okay? And the degree of this polynomial is 1, so therefore C is 1. I determine log B of A. Well, B is 3, A is 2. Log B of A, yes, you are allowed to use a calculator in an exam where you have the base log, right? And I determined that it's 0.63. And then I find out that log base 3 of 2 is actually less than 1, right? Based on what we calculated as 0.63. Then master theorem says, oh, your log B of A is less than C. Therefore, your algorithm is theta of n to the C. So what was our C? C is 1. So we determine, actually, we are in case number 1. So this algorithm that I have written turns out to be a theta of n, not a bad algorithm at all. So if you look at the algorithm that was representing those recurrences that I have given you, interesting ones where I am dividing by 3, calling it 2 times. If you thought it was looking like a silly algorithm, it was actually growing linearly, and it was not bad. Any questions here, right here? Any
Wait,
question?
professor. So,
Yes,
you are saying like this is case one, but like which one is case one?
we're going to go through the cases in a second.
Oh,
So there are 3 cases. So it shows, look, can you look at the blue rectangle here, blue greenish rectangle?
yeah. So the first one, like A
Yeah,
less than
yeah, yeah.
C
Do you
is
see log B of A is less than C,
I
then
see. I
T
see.
of N is element of big theta of N to the C. What is C? C
Yeah,
is
yeah,
1. So therefore, T of N is element of big of N, theta of N. So let's take a look at this cases. Do not worry, everybody. Do not worry. I always give you the master theorem. Always will give you the master theorem in your exam. You don't have to memorize it. However, it's not too difficult, honestly. So if you're going through a technical interview remotely, put it somewhere on your wall. You guys kid with me right now, but then I get emails later on say, I'm so glad you told me this because it came up and it was on my wall while I was talking to them. I was able to determine my runtime. I will give you the master theorem. You don't have to worry about the master theorem, memorizing it. Here are your cases. Log B of A is less than C means T of N is theta of N to the cth power, as long as you figure out what power your polynomial is. We know. We just looked at the example. Theta of N means N to the first power, therefore C is 1. Okay? Log B of A equals to C itself, then what you are doing is your theta is determined N to the C, whatever C is, log N. And that's where our merge sort is going to fall into. Log B of A is greater than C, then T of N is, in fact, a complexity class of theta of N to the power of log B of A. Okay, so what does it mean? People at MIT, I told you this, this is the general books that people use. Almost every university in the United States use this book as their elementary book to understand data structures. They pretty much worked on the master theorem. They have a proof of it there too. For my students who are interested in the proof of how it's being written, it's all there. Take a look at it. It's quite mathematical, but you will get a kick out of it. So what does it mean? If you are mapping into case number 1, where your log B of A happens to be less than the non-recursive work, recursive case does a lot of the work. And recursive case does a lot of the work than the non-recursive work. So that's where the actual work is happening. All right. If you have a situation where log B of A equals to C, recursive case evenly splits between the non-recursive work. So you have some other algorithms, f of n in this case. I just showed you an example where I had a printing statement that was n. So if I end up in case 2, that means my printing statement is working as hard as the recursion itself. If I have a situation where log B of A is greater than C, then the recursive case breaks inputs apart quickly and doesn't do much on non-recursive work. So this is the one that where I'm actually the recursion is heavily. Okay, so this causes your bottom of the call stack, meaning most work is going to be happening on recursion, and we're going to talk about that. So let me take you. And we're going to use this master theorem. There will be other examples I will bring and put it to you as problem solving. We're going to talk about an algorithm, which we're going to use master theorem to solve it. But this time, instead of having the input, we're going to supply the constant size input, okay, merge sort. So we're going to give the input, and then what we're going to do is try to come up with a algorithm that sorts a given array, okay? So the merge sort is an excellent example of divide and conquer. The input is going to give it to us. It's a small array. I'm giving you an array size of 10. You can have millions of records if you're trying to sort it. Merge sort is your first sort to step away from insertion, selection, and bubble sort. Those tend to be grow quadratically. We will talk about that. This is your first sort that you're learning that is going to, spoiler alert, is going to run in n log n. And for a sorting algorithm, that is a fast sorting outcome that we would like. For sorting algorithms, we would like the performance to be in theta of n log n, okay? So here is an array, taking the whole input size. What we're going to do is divide and conquer. We're going to divide our arrays into 2 halves. We're going to work on the first half, keep dividing. We're going to also work on the second half. That's why you have 2 recursive calls that is working on the same input size. Input size is constant, okay? I'm going to keep dividing until I have no elements or 1 element. Everybody writes this slightly differently. When I get to 1 element, you're going to see my algorithm in a second. If the input is less than 2, that means I have only 1 element. That is considered sorted itself, and then I will merge it back up. Okay? When I merge it back up from my recursive calls, I'm going to end up with a sorted list. So divide, conquer, combine. Merge sort is an excellent algorithm to show you how it works. It actually works. You guys always wonder, there's something off with this algorithm. There is nothing wrong with this algorithm. It works. And I have given you the merge sort, and you will experiment it yourselves on project number 3. We usually give you merge sort. My merge sort is not in place, meaning in place, new terminology alert for my students here, that I am allocating 2 half of a list here. I'm warning you that this is not in place. It eats up additional memory. Inside of my function, I declare 2 half of a list. Size of the original size is s, 2 halves. That makes a brand new list for me. So I'm adding additional memory to my computation. but you can write merge sort in place too. We'll talk about that. Let's talk about the algorithm first before we jump and go ahead. All right, here's my merge sort. I'm going to determine the length of my list. And if the input is less than 2, I have nothing to do. The list is already sorted. Done. Otherwise, divide my array by half. Assign the first half of my array to a list called S sub 1. Assign the second half of my array to a list called S sub 2. So S sub 1, S sub 2, when they add up together, I am using an auxiliary array to put my entire original array into it so that I have the sorted result. Okay, so that S sub 1, S sub 2, when they are added, it occupies the exact same size of my original array. So I'm using an additional array to solve this sort. Merge sort has that kind of reputation. However, it can be written in place. You will see that, and we will talk about that. Okay. So therefore, after I divide it into two halves, I make two calls to merge sort. I make a call to merge sort with S sub 1, first half of my array, and then I will sort that half of my array. Then when I'm finished with that half, because I'm going to keep dividing until I have one element and then combine it back up, it's all going to come up in a sorted manner. S sub 1 will be finished. Then I will make a call to the second half of my array, divide until one element, and then merge it back up. That merge it back up is where you're doing the sorting. And when I'm finished, I will have a sorted array. That's it. When I'm finished, I will have a sorted array. So what is this merge then? That's another function that you're writing. Merge function is the one that your recursive call will make a call to it in order for you to merge it back up. So you have your array, you cut it in halves, and you're working on the first half. You take that one, you cut that one in half. You take this one, you cut that one in half until you have one element. I want you to think of merge sort as an unfinished March Madness bracket. Okay? Start with 64 teams, if I'm not mistaken. I absolutely love March Madness. My students know that about me. Starting with 64, I go to 32, 32 to 16, 16 to 8, 18 to 4, 14 to 2, and eventually one winner. Okay, that's unfinished merge sorts because, in our case, we keep dividing until one, and then we merge it back up in a sorted manner. We just don't do that in March Madness. So we divide it all the way until one element, and then we merge it back up. So what if there are two elements? We will call the merge method. We are going to find out how we're going to sort those two elements among themselves. What if I have four elements? We're going to call the merge method. Now I have two elements that are already sorted in this sublist, two elements in this sublist. I'm going to merge them in by comparing them. From which sublist to pull from, okay? From which sublist to pull from, so I can create a new list of four elements that are already sorted. Then I take this four and another four that I have just worked with due to recursive calls, and I compare those two. That's what this is. It's comparing which sublist to pull from, okay? And I will bring you an animation of merge sort the next lecture. I'm running out of time, so you get a visualization. We will also have the debugging of this too, so you get an understanding how this merge method is working. But that brings us to determining the recurrence, okay? My dog just showed up and he's just checking. So I have my recursive algorithm, two recursive calls. I got some non-recursive work happening there. I have my base case, and then I have a method called merge. I peek at my method called merge. Oh, that's a method call is going as far as the input size. That's a linear algorithm right there, theta of n. Now my job is, the big job right now for this lecture, how can I determine the recurrence to represent my merge sort so that I can solve using the master theorem, perhaps, to determine its asymptotic analysis. So I look at my merge sort and I say, okay, it's time for me to figure out the recurrence. When we divide this entire thing, into steps, how our algorithm is breaking apart, I look at my base case immediately. This is my simulation of the merge sort. Let me show you how that's working. We start out with a very small Python's list that contains only 5 elements divided by half. S sub 1 is containing 8, 2. S sub 2 is containing 57, 91, 22. Work on S sub 1 divided again. Oh, 1 elements. I hit the base case. 1 elements are already sorted among themselves. So I call merge with 8 and a 2. I have to have 2 things in order to merge. I compare 8 and a 2. I put 2 in the 0th index. I put 8 in the first index. That sublist is already sorted. I go back up. That's how the merge is going to happen. And I work on my recursive calls on the second half. I divide until I have 2 elements, 91 and 22. When I get down to 1 elements, those are recursive calls that stopped. And I will call merge with 91 and 22 and then sort among 91 and 22. That becomes 22 and 91. That portion of the array is already sorted. I merge back up. And then when I bring it to here, of course, now you have 2 sublists that are already sorted among themselves. Sublist 1 is 2, 8, sorted among itself. Sublist 2 is 22, 57, 95, sorted among itself. Now, compare 22 to 22. Which one is lesser? Take 2. Move the pointer to 8. 8 is less than 22, put 8. You're done with that. Get the remainder. Remainder is just carried on to the final product. So that's how the merge sort is working. What is the recurrence? I have constant amount of work here. I have algebra here that I'm dividing it by half, doing some assignment operation. 2 recursive calls here. I have a call to a method that runs in linear time. So constant work, when n equals to less than 2, you can represent it as theta of 1. 2 recursive calls with n over 2, you're only working with 1/2 of the array, and a merge method, which is a linear time. More formally, I can represent it like this. Theta of 1, 2tn over 2, theta of n, okay? So if that's the case, now I'm asking you if you can analyze it for me. Can you use the master theorem to solve this?
Yes.
Yes. Should we do this together using the master theorem to solve this? Okay. What is A? It's a question for you. What is A?
2.
2.
What is B?
2.
What is log B of A?
1.
Log 202 is 1, right? You guys recall this? Yeah. So what is C? Well, I spoiled it.
1.
1.
Well, I spoiled it. Okay, log 202 is 1. So which case?
2. Case 2.
2.
Case number 2. I heard somebody speaking like case number 1. It's not case number 1. It is case number 2. Log B of A equals to C. Log 202 is 1. 1 equals to 1. So we are in case 2. What is the runtime complexity for merge sort?
N log n.
Thank you. I thought that you guys waited too long to answer. It is n log n. Look, aren't we case 2? Isn't this case 2, everybody? What is C? C is 1. So what is my merge sort then? Theta
N
of?
log n.
Yeah. Yeah. For a sorting algorithm, this is divine. I have written a sorting algorithm that is n log n, not quadratic. Not something you learned in 231, 232, where you're doing insertion sort, selection sort, okay? Merging example goes like this. I'm gonna let you go. I know. It's 11:40, just 1 more minute. You have 2 sublists that are gonna be sorted among themselves already due to merge. I'm gonna show you an animation next time we meet, I promise. Make a comparison. Take the small one, keep going, keep advancing, make a comparison. And if you run out of one array, get the remainder automatically because it's guaranteed. it's guaranteed that it's going to be bigger than the subset 1. Okay, just copy them over. That's how it works. It works. It does not fail. And we're going to go over it again. So riding with that, I want you to please pay attention, letting you go here, that non-recursive work actually matters. I had a non-recursive work in merge sort that was and. It matters, okay? So don't ignore those non-recursive works in your algorithm, like the one that I gave you in Recurse 2, okay? So I know I ran out of time. I'm gonna stop here. We have more recursion to talk about next week because your project number 2 and 3 depends on your skills understanding recursion. Thank you for coming, everybody. Sorry you had to go through technical difficulties. It happens. So stay cool. I'll talk to you. I'm going to stick around for a few minutes if you have questions, but I'm going to stop recording now. Thank you.
Thank you.
Thank you.
Bye, Jacob. You don't have to stick around. You can go now. Thank you.
Oh, I'm getting over to B for like 10 minutes, so I'll just hang out.
Oh, okay. Thank you. Let me stop the recording to get the Zoom. Sometimes it doesn't let me see the menu, which is very annoying.